All right, hopefully the recording's working. Cool. Today we're gonna talk about Elixir. Um, I guess a bit of a history. I've been doing Elixir on and off for quite a few years now. I think I started quite a few years ago when Elixir was just sort of in its infancy and was sort of born out of the Ruby community. But having said that, Elixir and Ruby are very, very different. Elixir actually does share a few things with Clojure, which I'll get to in a second. Just a disclaimer, this session is not about the in-depth Elixir functionalities. It's more so, what are the cool things that I think people might be interested in. Just to give you a taste of what Elixir is like, and maybe by the end of the session you'll be curious enough to look into it yourself. So here we go. Now Elixir, as we know, it is a bit of a niche, just like Clojure is. Having said that, there are a lot of companies using Elixir. So Discord, Pinterest, they both have millions of monthly active users, right? In Discord's case, they've got 11 million peak concurrent users. That's a lot. And in Discord's case, I think they use Elixir for those concurrency functionalities as well. And a lot of people might not realize that Slack, specifically their voice and video calls, are actually done by Elixir as well. And I think I was looking it up the other day. Spotify, one of the lead engineers from Spotify, wrote an article around how they actually switched from a JVM-based backend service to Elixir, just for one of their services, not the entire platform, but still. And when we're talking about Elixir, I'll sort of get to the Erlang part of it as well. And in this case, both WhatsApp and WeChat, they heavily rely on Erlang's concurrency to support the billions of monthly active users, which is it's pretty crazy to think about. So Elixir and Erlang, why are we talking about Erlang if we're talking about Elixir? The primary reason is because Elixir, if you think about it, it's a syntax layer on top of Erlang, if you will. So basically what it means is just like Clojure to Java or JVM, Clojure is a layer, running on top of the Java virtual machine. Elixir is running on top of the Erlang virtual machine, which is called Bean. The cool thing about this is that in Elixir, we can actually use any of the Erlang libraries, and we can call the Erlang functions directly within Elixir as well. They're 100% compatible. Now, one thing that's pretty unique to Erlang, certainly when Erlang was invented, I think 35 years ago, but even to today, I think is the model, right? In Erlang, everything is a process. Processes are strongly isolated, which means that states are actually kept separately per process. Process creation destruction is a lightweight operation, which means that it's decoupled from the underlying operating system's processes, and that's actually really important. And then finally, message passing is the only way for a processor to interact, which means that this is how Erlang supports scale, right? Now, speaking of message passing, I'm going to dive into the very first concept of the day, which is the actor model. I don't know whether anyone's heard of actor models before, but this is essentially describing Erlang's messaging system. So this is what an actor system looks like. You've got essentially actors passing messages to each other, right? And this is the way you essentially ensure that actors can exist almost like independently to one another, because you can't actually mess up the states. The only way to pass data or information to and from each other is through that messaging system. Later on, we'll kind of look at an example, but the interesting thing is that the other day I was reading the closure documentation, and I found this snippet directly from Clojure's website. It says Clojure may eventually support the actor model for distributed programming, because it's actually a very established and recognized model for distributed programming, right? If we go back a slide, just imagine that those actors or processes, if you will, they don't necessarily need to exist on one single physical instance, right? Especially in the sort of serverless sort of movement where, you know, the option is you can actually have multiple instances to, you know, to scale horizontally and to do the load balancing, right? To have a load balancer. Or you can use something like the Erlang system where you can have an Erlang cluster that load balances itself and scales itself, which is really, really cool. Now,
where are you saying the actors are in the more than one instance of each actor?
No, actors themselves are unique. So I think one way to describe it is that they are a identity, or they're an identifier, right? So you don't really need to duplicate actors, but you can actually distribute actors so that you don't need to worry about the underlying architecture or the underlying sort of infrastructure to support those actors, right? So if you think about how in many other environments, let's say JVM, right? You run a JVM on your computer, and your CPU has a limited amount of threads. So you can actually rely on those threads, or you can rely on JVM's green threads. But how would you scale beyond that one physical box, right? The language or the virtual machine itself doesn't necessarily have any support for that. So you have to rely on, you know, the more traditional way of you know, deploying onto multiple EC2 instances or ECS instances, and then do the scaling that way. But in Erlang, it's an option. You can do it the traditional way, or you can just rely on Erlang's built-in cluster and, you know, having those what we call the different Erlang nodes to talk to each other and pass messages to each other.
Okay, thanks.
Yeah. So the second concept, supervision trees, is actually related to the first one. So, you know, we've established that in Erlang or in Elixir, you can have, you know, multiple actors or /processes /nodes to form this cluster, right? And it's very, very trivial and simple to scale out that way. But how do you manage those different processes, right? What if one of the processes crashes, right? What happens then? So this is where a supervision tree comes in very handy. So what it is really, it's a tree structure, right? You have a you know, different kind of nodes forming up this supervision tree, and you can have any arbitrary amount of supervisors, those green dots, or workers, the blue dots. Now, there's actually no sort of there's not a lot of difference between, you know, why you would choose a supervisor over a worker, right? The only difference is that a supervisor will supervise another sort of node, in this case, another worker or another supervisor. That's the only difference. But the cool thing about this is that there are different strategies that you can actually apply to those individual supervisors or workers in the event that they crash, right? So if one of the worker crashes, you can choose to ignore it, or you can choose to restart that individual worker, or you can choose to restart all the workers belonging to the same sort of layer, or you can do some other, you know, things as well. which means that it is actually a super flexible system. And many people actually refer to this architecture as a self-healing architecture, right? So because when one of your nodes is having issues, you can do anything you like to actually repair it, or just to ignore it, or to sort of replace it with another healthy instance, which is really, really cool. This is actually built into the Erlang ecosystem. Now I'm going to switch gear a little bit. This is a really, really underrated functionality, in my opinion. And it's not unique to Erlang or Elixir, right? Other languages like Python has had this concept for years. So doc tests, what are they? Effectively, they are embedded comments that are executable. So when you look at this example, right, we've got the @doc, which means this is an inline documentation for this function. And all these lines of code here, they are actually executed within the unit test. So when you run the unit test, once you specify that you want to run the doc test for this particular module, these lines will actually get executed. And these are, the true, false, and unknown. These are the return values for each line. And if you specify a wrong value, the unit test will fail. Now, you might not think that's a big deal. Like, you can do it in the test file instead, right? You can. But what I found is that because they're in line, one is that when you're actually reading through the source code, you don't have to jump in between the source module and your test file in order to understand the correct inputs and outputs. But also, because the documentation is so easy to write and so easy to run, it actually helps you to think about how you would structure your code. One of the things about doc tests is that it only runs on public functions. So if you were to have a private function and you want to test it, well, you can't actually use doc test for it. So in that case, it kind of forces you to think about, how much logic should you actually put in the private function, or you might actually move the private function into another different module and make it public so that you can actually test it in isolation. So this is really, really underrated, I think. I just love it. Anytime I work on a sort of function, I first think about how testable is it. If I can't actually write a doc test for it, it's too complex. And sometimes the complexity is warranted, but a lot of times there are actually ways to simplify your functions.
It's a bit like the comment blocks in Clojure. So you can, like in Clojure, you can evaluate blocks of code.
Cool.
And send it to the REPL.
Yeah.
So often you see like comment blocks in code where it's just a REPL interaction.
Yeah.
Is this kind of like a REPL interaction, like these values here?
It
like,
is, yeah.
Is that IEX? Is that like the, okay, that's the prompt.
That's correct. So yeah. IEX is, yeah, so that's the REPL. Yeah.
Yeah, okay, cool. Nice.
Cool. Now, on to the next concept. This is probably the most popular or the most well-known concept out of Elixir. That's pattern matching. Now, pattern matching is so powerful. It's so powerful to a point where whenever I go back to a programming in a different language that doesn't have pattern match, I miss it. Because let's look at a few examples, right? So this is a very simple example of pattern match, right? It basically matches on the argument value or type and depending on the matched value or data type, it'll actually execute a different, I guess, copy of the function, right? So in this case, you first match the string value, and then if it doesn't match any of the specified string values, then it defaults to the third option, right? So that's the simplest form of pattern match, which it's not really advanced or interesting. So let's take a look at another example. So in this case, we're matching based on data type. So what you're looking at, person blah, these are maps. And the first three sort of function copies, they pattern match based on, I guess, the key and value of the map. So person, and then you've got the value, and the underscore name just means anything that doesn't match the previous value, and then you can match against the key as well as just arbitrary things, right? If it doesn't match anything, it'll go to the fourth option here. Now, you might think, well, you can probably use other things. In other languages, you can overload your functions and so on and so forth to achieve similar results. In this case, you probably can't use function overloading, but there are other ways to sort of mimic this behavior. But pattern matching is actually throughout the Elixir ecosystem. So it's not only used in functions. So here is another example that does exactly the same thing as the previous example. So instead of having 4 function definitions, we just have one, but we just have a case statement. And in this case, anything that goes into the case statement is also a pattern match, right? So pattern matching, it's throughout Elixir, which brings me to the next point, which is assignments. So typically, in a programming language, one of the simplest things that you can do is to assign a value to a variable, right? It's a very simple concept. It's a concept that's been done to death. In Elixir, we actually don't have assignments, believe it or not. There is actually no assignment concept. Now, I'll give you this example, right? This is valid Elixir code, right? It evaluates fine. Full name equals, a concatenated version of your first name and last name. It's really simple. You might think, well, you're assigning this string to the variable full name. And many new Elixir devs actually do think this is the case, but it's actually not. What this line, the full name equals first name, last name, what this line does is it does a pattern match, right? So basically it matches a variable to a value. So in this case, because full name was never matched before, it doesn't have a value. Therefore, it matches the string value of first name, last name. This is how it works under the hood. There is another example, right? This one shows you that it's basically doing the reverse of the previous example. So we've got a full name. We use string split to split the full name into a list, right? And in this case, on the left-hand side, we specify what we want to match the list against, right? And then we have first name, last name, so they get matched, and therefore we can return it as a map in this case. So this is actually a really, really powerful thing because it's not a simple assignment, it's a pattern match. Therefore, you can actually apply it to really, really complex data structure, right? You can even, one of the things I usually do is that you if you've got a return value that's, a very complex map, instead of, assigning that map into a variable and then sort of try to, navigate or traverse the nodes to get a certain value, you can just use pattern match to do that. And it's really, really simple, and it's really sort of easy to read as well. So this is a very, very powerful thing. Another powerful thing, or another thing that Elixir is known for, is pipe operator. So let's take an example of, printing your name, right? Let's say we've got a keyword list here. We've got title, we've got first name, we've got last name, and we basically want to grab the values of each keyword and concatenate them and just print them out and essentially upcase them as well. So one way to do it is to sort of almost like read right to left or sort of inside out. In this case, you look for the arguments, you get the values out of those arguments first, and then you do a join to form a string, and then you upcase the string, right? So that's one way to achieve it. And obviously this is, valid Elixir code, so you can do this in Elixir and in many, many other languages as well. Alternatively, if you don't like to read things from right to left or inside out, you can assign them to variables, right? Or in this case, they, pattern matches, but, you have your values, you've got your string, and then you upcase your string. So that kind of makes sense as well. In Elixir, the default way of doing something like this is like this, to use the pipe operators. What pipe operators are is effectively, it pipes data from, in this case, sort of top down, if you will. So args get passed into keyword.values, right? And the return value of keyword.values get passed into enum.join as the first argument. And then similarly in return, the return value of enum.join gets passed into string.upcase as the first, and in this case, only argument. So if you think about the data flow, effectively args in this case kind of just travels through those three layers and pops out at the end. So this is a really, really simple way to not only give you an option of, I guess, the simplicity, but also you don't have to, have, a bunch of temporary variables. You don't have to, read code sort of, in reverse orders or anything like that. It kind of just makes sense. So this is really, really, the concept is really simple, right? But it's actually really, really helpful and powerful in the day-to-day.
Does it have to be in the first position?
It does, yes. Which also means that it kind of forces you to think about your APIs, right? Because if you need args, or if one of the functions require args as a second argument, then it breaks this flow. So in this case, it kind of forces you to consolidate or to make your APIs consistent.
Yep.
So this is a very simple way to control, I guess, almost like a straight line kind of data flow, right? So args flow straight into these three functions. But we know that in programming, it's often not that simple, right? You've got different control flow logic. That's why we've got, if statements and case statements and so on and so forth. Now, in Elixir, we also have case statements. As you saw earlier, we have if statements as well, but we don't actually typically use if statements. And one of the reasons is because we have something cooler than just an if statements. We have something called with, and it's I guess it's to control your logical flow. Now, let's take a look at an example, right? Again, this is Elixir, it's non-conventional, but it demonstrates that in a lot of programming languages, you rely on having if and else or else ifs to determine those separate sort of logical paths, right? So in this case, we're talking about, whether you're ready or not. And what determines you to be ready is for wake up to be true, for wash up to be true, and for coffee to be true, right? Otherwise, it'll return false. Or if any of them are unknowns, then it'll return unknown as a result. So in if statements, it looks something like this, right? And this will be pretty universal for a lot of languages that use if statements. Now, in Elixir, we can do something like this instead. This is a Elixir condition. What that means is that instead of having if statements or nested if statements, a condition is a flat structured logic control. It means that if the first condition is true, you return something. If it doesn't, it goes to the second line. It tries to match that. If the second condition is true, it returns the value. And if it doesn't match any of those two, then by default, which is true in this case, we want to return false. Now, I know it's a bit weird to look at this way, but that's one of the ways that we can do it in Elixir. Now, the interesting thing is that condition is not with, right? It's just something that I guess something that could potentially replace if statements. But in Elixir, what we would do instead is this. Now, it might look really weird at first, but let me explain. So what with does in this case is it'll try to, you'll notice that the first three arrows, they're pointing from right to left, whereas the other two are pointing from left to right. I'll explain why that's the case. So in with, we actually do somewhat read from right to left. And the reason for that is we look for wake up, right? And then pattern match it. Again, pattern matching comes in play. Pattern match it against the value that's on the left-hand side of the arrow. So in this case, it'll check whether wake up matches to true. If it does, it goes to the next line to try to match wash up against true. If it does, it then goes and tries to match coffee against true. If all three are matched, are successfully matched, then in this case, we simply return true. If it doesn't, then there are options. If it doesn't, it means that if you think about almost like, the cursor working through with line by line, right? So if wake up doesn't match to true, what doesn't match it to? Is it false, or is it unknown, or is it something else? In this case, if any of the pattern matches don't get matched up and they actually match to unknown, then we'll return unknown. Else, we'll just simply return false. So basically, with in this case is almost like pattern matching plus the control flow on steroids. It's so powerful that you can actually do a lot of things with it. Now, this is a very simple example. Let me give you a real world example. So this is a code snippet I took out from one of my open source projects. So it's a web scraper, right? And what this function does is it does validation. So it checks whether the scraper or the web spider should actually scrape a particular link. So in this case, we've got like 4 checks that we perform, whether it is actually within the fetch depth, whether it's an acceptable URI scheme, whether we've actually fetched that link before, and whether we actually need to apply any filtering, right? Now, the cool thing about the width is that when we design our functions, so in this case, those 4 separate functions, we can design them in a way that they always accept the same arguments, in this case, options, and then they always return the same data type as a return value. So in this case, we're returning a tuple, right? And the second value in the tuple is Boolean, like it's true or false. And the first value, if we look at what's in else, is the type of the failure, right? So if it's false, it means it failed. What that means is that we can rely on using this width control flow and use pattern match to actually safeguard and to essentially do this sort of line by line flow, right? You check against whether it's within the fetch depth. If it matches true as a second value of the tuple, it goes on and goes on and goes on. Now, if it's not within the fetch depth, what do? Well, we return a tuple with the fail type. And so do all the other 3 functions as well, which means that in our else block, we can simply match against the tuple to find the fail type. And then, in this case, we probably raise an exception with the type of failure.
Does it run the second or the third pattern matches if the first one failed?
It doesn't.
Yeah. Cool.
Yeah. So this actually, imagining doing this in an if statement, like you have lots of ifs, right? You have lots of nested ifs, that is. Moving on to next topic, agents. Agents, I believe in this case, it's quite similar to closure agents. So effectively what they are is a way for you to store states. So in this case, I did a really simple save and load, right? You're saving the state in an agent, and then you can load the state from the agent. And agents can be named. In this case, we're naming the agents as match able, but you don't have to. Like by default, it takes the processor, the process ID as the name of the agent.
Fred, you got name and it's got the colon after, and then you got magic 8-ball, the colons before it. What are those? Like,
so these highlighted things are called symbols. So symbols are essentially almost like a pointer. It basically never changes value. It never changes their memory space. So they constant. So once they're assigned, they're always there.
So they can be on either side of the value, the symbol. So the colon can be on either side, is it?
Oh no, the column is what determines it's a symbol. So it has to start with the column.
Okay.
Yeah.
And the name, that name colon, that's also a symbol?
Oh, I see what you mean. So the name column is it's basically a keyword. If you think about in Ruby, you've got the hash maps, and then you've got that shortcuts with the colon as well. It's very similar to that. So in this case, name magic ball, match a ball is a keyword list. So basically, a keyword list is a list. Yeah. Now, similar to agents, sometimes we want to do things asynchronously, but we don't care about the states. In this case, we can use tasks. And this is something that's, it's basically a syntax sugar for the underlying sort of process-driven architecture. Because in the beginning of the session, I mentioned that, it's all about the actor model, you passing messages between different actors, right? This is what it does. But task just makes it easier for a programmer to do it. Now, this is really powerful in the sense that, when I did the merchant name sort of parser, I effectively rely on tasks to actually do those matching concurrently, right? Now, the interesting thing is that because in the beginning, it was mentioned that processes are strongly isolated, right? What that means is that, for us to process, let's say 2 million of records, if you want to process that concurrently in different processes, it means that those 2 million records need to be duplicated in each process. So in my first iteration of the merchant spreadsheet parser, that was my first option. I just duplicated the spreadsheet, and it turns out 16 gig of RAM was nowhere enough to do that. So this is something to be aware of. But the advantage of having those data duplicated is that you never run into race conditions, because a piece of data won't actually get access across processes that way. Now, this is a somewhat advanced topic. I won't go into too much details, but this is really cool. Now, there's a concept called Genstage, which I won't go too much into the details. I'll just explain in one sentence. Genstage is a specification for exchanging events between producers and consumers. So if you think about it, it's kind of like an event-driven system, right? And if you look at this diagram, it looks like an event, sort of event bus, right? Now, this in itself, there's nothing special. Typically you have, a producer produce a bunch of data. That data gets consumed by the second producer consumer, and gets passed on and passed on and passed on. Eventually it reaches the consumer, right? So that's very typical. So why am I so excited about this? And what does it mean with back pressure? Now, the cool thing about Genstage in this case is that it's not a push system, it's a pull system. What that means is that it doesn't really matter how many records the producers can produce. By default, it won't actually produce anything unless there is demand from the downstream consumers or producer consumers. What that means in the real sense is that, you've got your consumer obviously having a need to consume certain data, right? So as a consumer, I get to dictate how many data I want to consume at a time. So let's say I only want to consume 5 records at a time. So unless I ask for another 5, my upstream producers won't actually give me more records than I can chew. So this is really, really cool. And this is really good for managing, I guess, essentially managing demand, right? So that's why we call this Genstage with back pressure. The back pressure is effectively to look at from the consumer side of view and sort of working backwards. And everything is based on the consumer's demand.
Does the producer just drop stuff if there's no demand?
That's up to you to determine. So you can either drop it or you can hold them in a local queue somewhere, right?
Right.
Yeah, so it's very flexible. Now, processes, obviously we've already touched on processes before, but I kind of just wanted to reiterate, the concept and show you a very, very simple example. So if we read the words here first, so Elixir's processes should not be confused with operating system processes, right? Because operating system processes, they largely dependent on your CPU threads and so on and so forth. Processes in Elixir are extremely lightweight in terms of memory and CPU. And then the next sentence, which is really cool, because of this, it is not uncommon to have tens or even hundreds of thousands of processes running simultaneously. And this is often on a single CPU. And as we kind of discussed in the beginning, you can actually scale this out horizontally onto multiple CPUs, multiple nodes, right? Which means that, if you run your program on a distributed Erlang cluster, there's no reason why you couldn't have millions, if not billions of processes. So this is extremely powerful and concurrent. Now, you look at the example, it's really, really simple. So what it does, it sends, so this is what actor model is, right? It sends data, in this case, it sends hello world, which is a tuple, to self. Self is describing the process ID of the current process. So it sends this tuple to itself, and then you do receive. By default, it just receives on the current process as well. So then again, it does pattern match, right? Does it match the first tuple being the symbol hello? It does. All right, we return the value. In this case, it's the second value of the tuple, world, right? So this is basically the fundamental building block of what Erlang or what Elixir is. Something else that's pretty cool is we've got a concept called an observer. Now, not to be confused with the observer pattern. It's not a pattern, it's actually a tool. So in this case, it's actually a GUI tool. So this is actually built into Erlang itself. It's not an Elixir specific thing, it's actually an Erlang thing. So anytime when you're executing a Erlang or Elixir process or application, you can fire up this observer. And what this gives you, in this case, what you're seeing is the supervision tree, right? So you've got process ID, 090, it's got a sort of child process 010, so on and so forth. So you've got a very it's like a bird's eye overview of your supervision tree, but it also gives you, you can see there are other tabs in them as well. So you can do your code tracing and so on and so forth. So this is really, really powerful tool to inspect what your application is doing at any given time. Another cool feature is registry. So what is a registry? It's a local, decentralized, and scalable key value process storage. The best way to think of it is it's like DynamoDB, but in Elixir, or in this case, in Erlang, right? What that means is that for a lot of very simple key value needs, you don't actually need another key value store like Dynamo or Redis or anything like that. You can just do it in Elixir. Elixir provides that registry option for you, and you can run it in memory, or you can persist them onto disks and then distribute them across Erlang, different Erlang nodes as well. So this is extremely simple to use and really, really easy to scale. So technically, we don't need DynamoDB. All we need is Elixir and registry. That's all we need.
How does it make sure that? So you got many agents running, or processes running, and they might update the registry at the same time, right?
Yes and no. So you can't update the registry at the same time. So in this case, it is actually really similar to what Clojure does. So a Clojure agent, you can't actually update the same piece of data from different sort of code paths, right? So in Clojure, it basically creates different snapshots to store those values. Therefore, you're interacting with different snapshots of the same state, or the original state, I should say. In Elixir, it's very similar. Like you can't have multiple processes sort of almost like editing the same piece of data, because data is immutable. So you can't mutate the data anywhere. So it always creates a new copy. Does that make sense?
Mm.
Yeah.
So the registry is local?
What do you mean by local?
I mean, is it a distributed, or like, I mean,
It can be. It can be. So it really depends on. So in this case, it's decoupled from how you sort of scale or how you deploy your system. So by default, I guess it is local in the sense that you can call the registry without doing much, right? In this case, all you need to do is look at what's in the init function. So registry start link, which actually starts a supervision tree for that registry. And it's bound to the current process. But it doesn't have to. Like you can because of the supervision tree and the Erlang clusters, you can run this or have that registry available to other like distributed nodes as well. The next concept is type specs. Now, this is another thing that Elixir and Clojure are really similar in a sense that they both dynamically typed, right? However, they both have an optional type system. So in Elixir, we have this thing called type spec, which is actually not part of your sort of default Elixir compilation flow. So by default, if you compile Elixir, it doesn't actually check your data types. But you can use type spec. So it's a separate tool to do exactly that, to verify or in compile time whether the types are actually correct. Now, a use case in this case is, again, this is taken out of my open sourced scraper library. So my scraper supports arbitrary parsers, right? So it's got a default parser, but I can actually, as a developer, you can provide your own parser to parse the page. However, your parser needs to adhere to certain specifications. In this case, the data types of your inputs and the return value, so the outputs as well. And in this case, URL needs to be a string, body needs to be a string, options needs to be a map, page needs to be a page struct, which contains URL, body, and options. And then you've got a return type of a tuple. So again, this is just something extra. A lot of people don't use it. Some open source libraries do to ensure you've got the compile time safety. But it's up to you to decide whether you want to use it or not. So here's another one that's also common in Clojure as well. Protocols. So Elixir also has protocols. Protocols are a mechanism to achieve polymorphism in Elixir when you want behavior to vary depending on the data type. So here is a very simple example. We kind of have a protocol called size, which defines a function called size, and then you can implement the function size for different data types. So in this case, one for bit string, one for map, one for tuple. This, if you haven't used a lot of, if you haven't used protocols in Clojure before, this is like really, really awesome for implementing things like a strategy pattern where, depending on, different clients, you might have a different module with the same set of interfaces for that particular client. So that's really, really simple way to achieve that. The last concept, which I won't go too much into the details of, is macros. Again, I believe Clojure has something very similar, right? It's for metaprogramming and having your own DSL. In Elixir, macros are sort of almost like discouraged in a sense that because it hides the underlying complexity away from you. However, because of how powerful it is also used throughout the standard library of Elixir. An example of which is that what you're looking at is a unit test. So Elixir ships with a standard unit test library called XUnit. So in this case, we use the XUnit case template. Now, from the syntax highlight, you can probably already tell that use is things like def module, use, do, and these are all reserved keywords of Elixir. What about the white ones? Dot test, setup, on exit, test, assert. These are all macros. And these are macros that, in this case, setup is to setting up your test cases. They get run before each individual test. On exit is the tear down of each unit test. So it's a really, really powerful way to define your own DSL. Last but not least, I've gone through all the cool sort of concepts in Elixir. Now it's time for me to do a bit of a plug. So when I just started sort of learning more about Elixir, I want to sort of learn and sort of practice those different concepts. So what I've done is I built a few open source libraries. The first one, OPQ, it's a very simple first in, first out queuing system with some cool features like rate limiting and sort of worker pooling and so on and so forth. I built that to support my third library here, Crawler, which is the web scraper I mentioned before. And Crawler is also pretty cool, I think, because if you think about what happens when you scrape a website, is that you look at the page, you determine the links you want to fetch, and then you kind of go a level deeper and deeper and deeper, right? It's the perfect use case for a highly concurrent system. So it's a perfect use case for Elixir in this case. And Crawler in this case heavily relies on those concurrency features to do the web scraping. And it relies on OPQ to do the queuing as well. Now in the middle, Simple Base is a machine learning library based on the naive-based machine learning algorithm. So it basically does the sentiment analysis. So based on certain data, it'll try to match the data and give you a result based on how close it is with your training data. So you provide Simple Base with a training data set. Once you're happy with the training data set, and you can apply the learned algorithm to a new data set and get the results out of it, which is pretty cool. And that's it. That's all I have today. Any questions? I'll stop the recording, but any questions?